morning. I am Sheetal from BSc Chemistry Honors second year. Today I am going to make audio recording for visually impaired students. Chapter number 4, Nitro Compounds. Introduction. Nitro compounds are an important class of organic compound which may be regarded as derived from hydrocarbons by the replacement of one or more hydrogen atom by nitro group. Nitroarenes, nitro compound in which NO2 group is directly attached to benzene ring, can be prepared rather easily and have been used as synthetic reagents since long. But nowadays, even nitroalkanes are being prepared and used on the large scale. Structure of nitro group. Nitro group is quite often represented as containing a double bond between nitrogen and one oxygen and a coordinate or dative bond between nitrogen and other oxygen. But actually nitro group is stabilized by resonance and is a hybrid of two equivalent contributing structure. The resonance hybrid structure is confined by the fact that the bond length of the each nitrogen oxygen bond is 1 to 1 picometer or 1.21 angstrom, which is intermediate between NO single bond length and N double bond O double bond length. In case of nitroarenes, resonance of nitro group with the ring can also be taken place, giving rise to additional contribution structure for the molecule. It will be interesting to note that nitro group is isoelectronic with carboxylate anion. Nomenclature of nitro compound. Nitro compound are named by writing the word nitro before the name of the parent compound. The number of nitro group and their position are also suitably indicated as illustrated below. Nitromethane, nitroethane, 2-nitropropane, 2-nitro-3-methyl-butane. Nitrobenzene, orthonitrotoluene, meta-dinitrobenzene, para-nitrophenol. Classification of nitroalkane. Nitroalkane are termed as primary, secondary, or tertiary according as the nitro group is attached to a primary, secondary, or tertiary carboatom. That is, primary nitroalkane, secondary nitroalkane, tertiary nitroalkane. For example, nitroethane primary, 2-nitropropane secondary, 2-methyl 2-nitropropane tertiary. Preparation of nitro compound. Preparation of nitroalkanes. Nitroalkane are usually prepared by following method. First is vapor phase nitration of alkane. This reaction involves the substitution of a hydrogen atom of alkene by a nitro group. It is carried out in the vapor state by heating the alkene with nitric acid at about 700 Kelvin. Alkane plus HNO3 at 700 Kelvin temperature give rise to nitroalkane plus H2O. Limitation of the process. During nitration of higher alkene, all possible isomeric nitro products are formed. Moreover, rupture of carbon-carbon bond also take place, leading to the formation of nitroalkanes containing lesser number of carbon atoms. For example, nitration of propane result in the formation of a mixture of 4 nitro compound as shown below. Propane in the presence of HNO3 at 673 Kelvin temperature give rise to four products. First is nitropropane 25%, 2-nitropropane 40%, nitroethane 10% plus nitromethane 25%. Due to the formation of complex mixture of product, this method is not used for laboratory preparation of nitroalkane. However, the method is widely used for the commercial preparation of nitroalkane since they are used as industrial solvent only. Mechanism. The reaction is believed to involve the formation of free radical, but the mechanism is not well established. Second, the action of silver nitrate on alkyl halide. This is the method generally employed for the laboratory preparation of nitroalkanes. When heated with silver nitrate, alkyl halide undergo nucleophilic substitution to form nitroalkanes along with small quantities of alkyl nitriles. This is because NO2 negative is an ambidended nucleophile. Alkyl halide plus AgNO3 give rise to nitroalkane major product plus alkyl nitrile minor product plus AgBr. Oxidation of amines. When amine in which the amino group is attached to a tertiary carbon atom is oxidized with potassium permanganate, a tertiary nitroalkane is obtained. Amine plus 3O2 in the presence of KMNO4 give rise to tertiary nitroalkane plus H2O. Preparation of nitroarenes. Nitroarenes are almost invariably prepared by direct nitration of arenes. The nitrating agent generally used are concentrated or fuming nitric acid. Second is mixture of concentrated or fuming nitric acid and concentrated sulfuric acid. Sometimes fuming sulfuric acid is also used. This mixture is most commonly used as nitrating agent. Mixture of concentrated nitric acid and acetic anhydride or boron trifluoride. Acetyl nitrate obtained by mixing nitrogen peroxide and acetic anhydride. Nitrogen peroxide in the presence of anhydrous aluminium chloride. Choice of nitrating agent. The choice of nitrating agent to be used for nitration of a given compound depend upon the following two factors. First is nature of compound to be nitrated. Second is number of nitro group to be introduced. In the nitration of aromatic compound containing electron releasing or activating groups such as NH2OH and CH3, the reaction takes place readily at room temperature by employing concentrated HNO3. In some cases, even dilute HNO3 can also be used. For example, phenol plus dilute HNO3 give rise to ortho and para-nitrophenol plus H2O. For nitrating compound containing electron attracting or deactivating groups such as C double bond OH, or when it is desired to introduce more than one nitro group, a suitably strong nitrating mixture has to be employed and the reaction is carried out at high temperature. It may be remembered that nitro group itself is also a deactivating group. Nitrobenzene and meta-dinitrobenzene, for instance, can be obtained from benzene under the conditions shown below. Meta-dinitrobenzene in the presence of concentrated HNO3 plus concentrated H2SO4 at 373 Kelvin temperature gave rise to metadinitrobenzene, and in the presence of concentrated HNO3 plus concentrated H2SO4 at the temperature of 328 Kelvin gave rise to nitrobenzene. Mechanism of nitration. Nitration of aromatic compound like other aromatic substitution reaction is electrophilic in nature and involves a nitronium ion NO2 positive as the attacking electrophile. This mechanism may be summed up as follow by considering the nitration of benzene with nitric acid sulfuric acid mixture. First is generation of electrophile. HNO3 plus 2H2SO4 at equilibrium give rise to nitronium ion plus H3O positive plus H2SO4 negative. Second is formation of carbocation ion. Third is proton transfer from the carbocation to yield the final product. Evidence in the favor of above mechanism. It has been shown above the aromatic nitration involves a stepwise mechanism. The nitronium ion, which acts as the electrophile reagent, is generated in a preliminary step and brings about further reaction in two steps. The first step is slow rate determining step involving the addition of nitronium ion to the aromatic ring to form a carbocation intermediate. The second step, which is relatively fast, involving the elimination of a proton from the intermediate ion by the heterolytic cleavage of CH bond. This mechanism have been fully supported by isotope tracer technique as explained below. If the aromatic compound labeled with deuterium, the heavier isotope of hydrogen having a mass of 2 AMU is subjected to nitration, it is found that the rate of substitution of deuterium ion is same as that of the ordinary hydrogen or plutonium. In other words, no isotope effect is observed. Chemical reaction of nitroalkanes. The important chemical reaction of nitroalkanes are as follows. First is acidic nature, tautomerism. Nitroalkane containing alpha hydrogen atom, it means primary and secondary nitroalkane only, exhibit acidic behavior and form salt in the presence of strong alkaline. For example, RCH2NO2 plus NaOH give rise to RCHNO2 negative sodium positive plus H2O. The acidity can be attributed to the fact that first is nitro group have a strong electron withdrawing inductive effect, and the second, the anion formed after the removal of the proton from nitroalkane get resonance stabilized due to the ability of nitro group to accumulate negative charge as shown below. It is interesting to note that if the salt formed by nitroalkane is acidified at low temperature, the oily drop of nitroalkane do not separate immediately, but we get another form of nitroalkane known as acinitroform, which slowly changes into the nitroform. This is due to the fact that primary and secondary nitroalkane exhibit tautomerism, the tautomeric form being nitro or isoform and acinitro or nitronic acid form. The tautomeric equilibrium between the two nitroform lie almostly completely towards the nitroform because it is stabilized by resonance of nitro group. Acinitroforms is relatively stronger acid than nitroform. An important feature of acinitroform is that it can act both as electrophile and as a nucleophile. Unlike primary and secondary nitroalkane, tertiary nitroalkane do not have any alpha hydrogen atom. As such, they exhibit neither acidic character nor tautomerism. Reduction of nitroalkane. Reduction of nitro compound is one of the most important reaction. The reduction of nitro group take place in stage as shown below. Nitro compound give rise to nitroso compound give rise to substituted hydroxylamine give rise to primary amine. The product actually obtained depends upon the nature of reducing agent and pH of the reaction medium. Thus, nitroalkane can form different product on reduction as given below. First is reduction in acidic medium. When reduced in an acidic solution, nitroalkane form primary amine. Nitroalkane plus 6H in the presence of FeHCl give rise to primary amine plus 2H2O. Second is catalytic reduction or reduction with LiAlH4. Reduction with LiAlH4 or H2 in the presence of nickel, palladium or platinum catalyst also yield the same product. Third is reduction in neutral medium. If the reduction is carried out in the neutral solution, a hydroxylamine derivative is obtained. For example, nitroalkene plus 4H in the presence of zinc NH4Cl give rise to alkyl hydroxylamine plus H2O. The hydroxylamine are readily oxidized to corresponding nitroso compound on warming with Tollens reagent which get reduced to metallic silver. The reaction is used as a test for nitro compound under the name Baker-Mulliken test. Baker-Mulliken test. Third is hydrolysis. When boiled with concentrated HCl or H2SO4, primary nitroalkane undergo hydrolysis to form carboxylic acid and the corresponding salt of hydroxylamine. For example, nitroalkane 1 degree plus H2O plus HCl in the presence of heat give rise to RC double bond OH plus NH2OH dot HCl. Secondary nitroalkene are also hydrolyzed to ketone and nitrous oxide by boiling with concentrated HCl. Nitroalkene 2 degree in the presence of boiling HCl give rise to 2RC double bond OR plus nitrous oxide plus H2O. Tertiary nitroalkene and nitroarene are not hydrolyzed by acid. Fourth is NAF reaction when sodium salt of primary and secondary nitroalkene are hydrolyzed by boiling with dilute sulfuric acid, aldehyde and ketone respectively are obtained. Action with nitrous acid. Primary, secondary and tertiary nitroalkane exhibit different behavior towards nitrous acid. First is primary nitroalkane react with nitrous acid to form nitrolic acid which dissolve in NaOH to produce a red solution. Nitroalkane plus HNO2 give rise to nitrolic acid plus H2O that dissolved in NaOH to give red color due to the formation of sodium salt. Secondary nitroalkane react with nitrous acid to form pseudo-nitrosyl which have blue color but do not dissolve in NaOH. Tertiary nitroalkene and nitroarene do not react with nitrous acid since they do not contain any alpha hydrogen atom. The above reaction can be used to distinguish between primary, secondary and tertiary nitro compound. Halogenation. When treated with halogen, chlorine or bromine in slightly alkaline solution, primary and secondary nitroalkane undergo halogenation at alpha position. For example, nitroethane in the presence of Cl2NaOH give rise to 1-chloro. Nitroethane in the presence of Cl2NaOH give rise to 1,1-dichloronitroethane. 2-nitropropane in the presence of Br2NaOH give rise to 2-bromo-2-nitropropane. The mechanism may be summed up as follows. Second is catalytic reduction. Reduction of nitrobenzene with H2 in the presence of nickel or platinum catalyst also leads to the formation of aniline. Third is reduction in neutral medium. When reduced in the neutral medium with zinc dust and ammonium chloride solution, the reaction stopped at hydroxylamine stage. Refer to the mechanism given above. Phenol in the presence of zinc aqueous NH4Cl give rise to benzyl NaOH plus H2O. Reduction in alkaline medium. On reduction in alkaline medium, nitrobenzene yield different product depending upon the nature of reducing agent employed. And nitrobenzene in the presence of Na3, ASO3, NaOH give rise to azoxybenzene. Nitrobenzene in the presence of zinc NaOH in CH3OH give rise to azobenzene. Nitrobenzene in the presence of zinc NaOH give rise to hydrozobenzene. These products are actually formed by the further reaction between primary reduction product nitrosobenzene and phenyl hydroxyl amine as shown below. Azoxybenzene A is formed by condensation of nitrosobenzene and phenyl hydroxylamine as given below. There is sufficient evidence to show that azobenzene B is formed through the intermediate formation of azobenzene and its further reduction. Hydrabenzene C is similarly formed by the further reduction of azobenzene. Fifth is reduction with LiLH4. Reduction of nitrobenzene with LiLH4 also yield azobenzene. Sixth is electrolytic reduction. When reduced electrolytically in weakly acidic medium, nitrobenzene gives aniline, but on electrolytic reduction in strongly acidic solution, nitrobenzene yield paraminophenol due to rearrangement of phenyl hydroxylamine first formed. Electrolytic reduction in alkali medium yield azoxybenzene, azobenzene, and hydrobenzene. Seventh is selective reduction. In case of compound containing more than one nitro compound, it is possible to carry out the selective reduction of one of the group by employing a mild reducing agent such as ammonium hydrosulfide or sodium polysulfide. This reduction is known as Ginin reduction. Third is electrophilic substitution. Nitro group, being an electron withdrawing group, has a strongly deactivating effect on electrophilic substitution reaction of benzene nucleus. However, under strong condition, nitro compound may undergo electrophilic substitution in meta position with respect to the nitro group. For example, metachloronitrobenzene formed in the presence of Cl2 FeCl3 from nitrobenzene. In the presence of fuming HNO3 concentrated H2SO4, nitrobenzene is converted into meta-dinitrobenzene, and in the presence of fuming H2SO4, nitrobenzene is converted into meta-nitrobenzene sulfonic acid. It may be noted that nitrobenzene does not undergo Friedel-Crafts reduction. Fourth is nucleophilic substitution. The nitro group has no doubt a deactivating influence on electrophilic substitution in benzene nucleus due to its electron withdrawing nature. But this very electron withdrawing influence of the nitro group make the benzene nucleus liable to be attacked by nucleophilic reagent. Thus, unlike benzene, nitrobenzene on heating with sodium hydroxide gives small amount of ortho and paranitrophenols. Mechanism. The mechanism of the reaction may be outlined as follows by considering the formation of paranitrophenol. Fifth is the replacement of nitro group. In case of polynitro compound, one of the nitro group itself can be replaced by nucleophilic group. For example, para-dinitrobenzene in the presence of 2 moles of ammonia give rise to para-nitroaniline plus N2 plus 2H2O. In the presence of KOH, para-dinitrobenzene give rise to para-nitrophenol plus KNO2, and in the presence of C2H5O negative Na positive, para-dinitrobenzene give rise to para-nitrophenol plus NaNO2.